Good afternoon, ladies and gentlemen. I'd like to quickly introduce myself. I'm YuxiangHe from NOVA. As a research scientist, I'd like to take this opportunity to talk about planetary boundary layer height retrievals from Cosmic 2. First, I'm going to present the motivation, and then I will show you with the methodology used in this study. And the last part, I'll show you the main results. Cosmic 2 was launched on the 25th June 2019. A receiver like Cosmic or Cosmic 2, which is on the low Earth orbit, tracks the changes in the phase of radio signals from 1 to 2 GHz, transmitted from GNSS constellations, for example GPS, GLONASS, Galileo, and the signals passes through different atmospheric layers. The phase delay measurement is directly related to the refractivity index of the medium, which is a function of temperature, pressure, humidity. Through the chains of GNSS constellation and its receiver, we can derive bending angle and refractivity index, and further get the gradient of them. GNSS-RO observations have a vertical resolution finer than 100 meters, and also which works for warm weather and warm conditions. Since early 2020, the NOVA NCEP operational numerical weather prediction system has started to assimilate the Cosmic 2 data. As we know, PBL is a key component of weather and climate system and air quality. This layer is an interface between Earth's surface and the free troposphere through affecting energy and mass flux. Look at this schematic diagram. During clear sky, the lower troposphere consists of a roughly sublayer, a surface boundary, a well-mixed layer, and a capping entrainment layer. The mixed layer plus surface layer typically is from 1 to 2 km, so its detection requires high resolution, at least lesser than 100 meters. And the entrainment, the one above the PBR height, is about 200 meters. It is thin, so it is a challenge with passive sounders. Meanwhile, due to frequent cloud existence, along with PBR, it is difficult to be detected with infrared sounder as well. Define PBR height we can from the perspective on turbulent motion, PBR dynamics and thermodynamics, or distributions of various substances in the PBR. To determine the PBR height, different methods can be used by means of direct observations and remote sensing retrieval. In this study, we are going to use the bending angle of Cosmic 2 to derive the PBR height by minimum gradient method. The sharp vertical structures between layers have to be smoothed away before we can further processing. The locally weighted scatter plot smoothing was applied to each bending angle profile, and then calculated the first and second derivative of bending angle within the most possible window, which is determined by analyzing climatic PBR height. The second derivative is used to find the minimum gradient of the bending angle. In our study, Calypso version 420 cloud layer and also ERA5 PBR height were collected, collocated with the occultation event position time in Yucca Cosmic 2 ATM profile data, and also used the following collocation conditions. The time differences are within 2 hours. The distance within 200 kilometers. When both conditions are met, the normalized pairing parameter is used to decide optimal pairing, and also only the profiles which penetrating deeper than 500 meters were considered. A case I presented here is a comparison of Calypso Cleo cloud top height and cosmic atmospheric boundary layer height. Plot A is a Calypso cloud top and base. The blue dots are cloud top. The red dots are cloud base. The blank line is the average of cloud top height. Plot B is the gradient of bending angle and reflectivity, the height of refractivity gradient. The red line in the plot has some shift comparing with Cleo cloud top height. So the gradient of the bending angle is a good indicator of atmospheric boundary layer cloud height. In the following section, I'm going to compare cosmic 2 PBR height developed in this study with Cleo cloud top height. And also, I'm going to compare our products with EAR5 PBR height. A case shown here is a collocated Cleo and GNSS RO track. In the left image, the dashed blank line is the Cleo track. The thick blank line is the Cleo track, which is within 200 km and a 2-hour window when collocated with GNSS RO track, which is the white line in this image. RO track and the occultation point located in the center of white line. The background color is from the brightness temperature. The unit is Kelvin, which comes from Go's image of 10 mm wind channel. In the right image shows a vertical cross-section. You will see a very clear transaction zone above the PBR height. The height is changing from 3 km to around 2 km. To reduce the possible cloud heterogeneity, for example, broken clouds, for GNSS RO Cleo pairs, and reduce possible uncertainties, only those GNSS RO Cleo pairs that contain more than 100 Cleo pixels, and where the standard deviation Cleo cloud top height in the ensemble relative to its mean is lesser than 0.1 km apart. In those 3 plots, the data comes from October 2019, the entire month. About 10,000 profiles were used. After collocation with Cleo and Cosmic 2, we just got about 200 RO Cleo pairs. You can see the Cleo low cloud height and Cosmic 2 PBR height in those pairs are very consistent. The mean bias between them is close to 0, and the standard deviation is 0.268. Correlation is 0.917. The midplot is a histogram of them. 2 lines represent the distribution. They have almost the same distribution. We also plotted the bending angle gradient for the paired profiles with respect to the altitude of the corresponding Cleo cloud top heights, the 0. The average is given by the red line, and the average standard deviation are given by the green line. The peak is about 0, which indicates the algorithm of cosmic 2 PBR height in this study is robust. To further investigate the possible difference over different ocean regions, the geographic distribution of cosmic 2 PBR height and Cleo low cloud top height are compared in the first row. You can see those distributions have a similar pattern, and also those patterns are related to sea surface temperature. And the three regions are analyzed with which are shown here. Clear low cloud top height and cosmic 2 in each region are consistent. There is no significant difference between them. In the following part, cosmic 2 PBR height compared with the ERA 5 PBR height, mainly focused on the diurnal cycle of the two products. The plot in this slide is showing the overall performance of the cosmic 2 PBR height relative to EAR5 PBR height. Left plot is the scatter density. The right plot is a histogram of them. You can see they are following almost the same distribution globally. This slide shows the comparison between cosmic 2 and EAR5 PBR height on different land surface types. The overall result is the diurnal cycle difference between land and water. It was noticeable that PBR height over land has obvious diurnal cycle relative to the PBR height over water. And the PBR height over desert shows greater diurnal variation than that over vegetation surfaces. Because of clear sky and no substrate water content in arid regions, which allow higher surface temperatures, resulting in stronger sensitive heat fluxes to the atmosphere and deeper turbulent mixing. Concluding, on average, the cosmic 2 PBR height is consistent with clear low cloud top height, and also consistent with EIR5 PBR height. The mean PBR height from cosmic 2 has similar diurnal variations with that of EIR5. The PBR height over desert has deeper variation than the over vegetation regions, but PBR heights over ocean show no clear diurnal cycles in terms of global average. GNSS measurements has fine vertical resolution, cloud penetrating ability, and moisture thermodynamics information about the PBL. The observation of refractivity bending angle is a function of temperature, pressure, and humidity in lower troposphere. It provides a new opportunity in determining PBR heights. Especially recently launched Cosmic 2, which provides more than 4,000 atmospheric bending angle and refractivity profiles each day. The Singer has a higher single noise ratio compared to other global navigation satellite system radio occultation missions and a deeper penetration than those from other RO missions. But we have to notice that current GNSS data are not very well suited in identifying and determining the depth of the shallow PBRs due to the data quality near the surface. Thank you for your attention.